Okay, folks, we're looking at our PC lab for 3D molecular editing, and I'm going to go you through the setup. And I'm going to do this on Windows, and I should have another video for those of you using the Macs. All right, so the three programs we're actually setting up are Avogadro, Falkio, and Firefly. Now, the Firefly requires registration, so it's not an immediately usable program. But down here at the bottom, I have an old version of Firefly, just specifically for Windows, that will work, and you won't need to register this one. All right, but I actually included these downloads, but there's no reason at all that you couldn't go right to the actual site. And I've already downloaded all those and got these ready to go. Avogadro is a neat little program that's going to help us with a lot of things, and it does these electrostatic potential maps really, really well. And then Falcio also does electrostatic potentials, just does it differently, but we're not going to use it for those electrostatic potentials. All right, but get a version that's appropriate. More than likely, you need the 64-bit. Avogadro, when you hit download, it's going to go to a site called SourceForge, and it will automatically detect what is the best version to download. And then Firefly, if you go here to downloads, you will see that it actually has a huge amount of, I agree not to copy this, terms of service. And then you actually have to search through all this for what you wanted to use. If you're using Linux, these programs down below are for your faster and faster computers, the supercomputers. But most of us are able to use either this unified serial for Windows or for the Mac. And I actually have the Windows version on that front page. All right, so all I've done so far is actually copied them ready. And I went ahead and installed Avogadro because it does take a little bit of time and I have a slow internet. So I'm going to start expanding these while we get Avogadro going. And that really is just because they were taking a while on my computer. And of course, it's making me a liar by working really fast. All right, while those are going, I'm going to go ahead and start up Avogadro. And we're going to go over it first. It's a totally separate program. It does things totally different. And borderline a little bit more user friendly, but not perfect. And we'll see what I mean by that as we're doing that. So what I'm going to do on here is actually just make a simple alkane. And I really am just clicking with my mouse and it's going to draw a methyl. Now, depending on the colors of your computer, that might look darker because it's supposed to be carbon. Carbons are typically black marbles and the hydrogens are white. And I'm just going to build a molecule. All right, I just put 4 carbons in a row, so I made butane. I don't want to do butane, that's a bit too boring. So I'm going to change this to an oxygen. All right, and now that little icon there that looks like the cross, that's my move things around. And the reason I did that is I want to try to make that a double bond. So we'll go back here, and theoretically, if I just click on that, all right, so you will find that Avogadro, it really has to have the perfect angle for seeing that, or else it's actually going to mess up. I'm going to try this. I'm going to, right, yeah, all right. So what I did was I just right-clicked on the hydrogen there, made it go away. And now I'm going to try to click on that bond. Yeah, all right, see? When I clicked on the bond with my left mouse button, I turned it into a double bond. Now, technically right now, this hydrogen is wrong because I made a double bond to that carbon. But if I go back here and just reselect carbons and then hit adjust, when I click on that, it'll fix it. Now, something else that's interesting right now, when I pivot this around, looking at that carbon I'm spinning on, it's got that trigonal pyramidal shape to it. Well, it's only got 3 things on it. It should be trigonal planar. Well, there's something that Avogadro does really, really well for optimizing the structure. So I'm going to go here to this auto optimization tool, and I really am just going to hit start. See how this number is dropping and such? What it's doing is it just actually rearranged the molecule to get it into its lowest energy. Now, here's something weird. I can still grab things and pull on it. and it's just gonna go right back to adjusting it and trying to get it in the lowest energy it possibly can. There. All right. I got it in a. It's gonna make that nice zigzag pattern we expect a alkane to do. And it's got nice little uniform structure to it. All right. Let's get this in a pretty location. Yeah, I think that's good. All right, now that we've done that, I want to show you that. So we just showed how to optimize the structure with that auto optimization tool, and I want to stop that because otherwise it's going to work against us and everything. What we're going to do now is draw one of those electrostatic potential maps. Now that was where it was showing all the electron density. Now we are expecting a big, huge red area around the oxygen because that's the electronegative atom. But the neat thing about generating your own is you can do it for any molecule and see how it is. So we're going to come here under extensions and do create surfaces. And van der Waals is fine, but we're going to color it by the electrostatic potential. And resolution doesn't necessarily matter. My computer's doing well enough. I just been putting it up on high. You notice how it went pretty darn fast. And unlike your textbook, which shows the neutral area in green, this will show up more like white. So we have the red where we'd expect it to be with that huge electrostatic potential around the oxygen. But the neat one are these two oxygens down below actually having some blue to them. And we will see later on. So in Orgo 2, we actually do study aldehydes and ketones, and we find out that the oxygen makes these hydrogens, those four that are on adjacent carbons, a little bit more acidic. All right, but that is what you're going to be doing on your own. But I actually want to show you something more to actually speed up the process some. All right, so right now I have a butane with a ketone in it. And if I go here to view and do properties and then molecule properties, it's going to look up the name. Now, depending on how fast your internet connection, that should already be done. And I'm going to give up here just a second. I know I have bad internet connection right now. Oh, there it goes. So butane 2-one. Also, name that we're going to see later on, the 2 could have been out in front, could have been called butanone. All right, but it actually figured that out itself. And we have a few other things it does in those properties that are going to come in handy later. So the conformer properties are something we'll look at it. We could use in class later, and some of the bond properties itself, because they really are going to show us bond lengths and such. A lot more information than we typically need, but very beneficial and somewhat. And then the other thing that we're going to find, we can do something relatively complex too. All right, so knowing that it can look up the name, something that Avogadro figured out how to do, let's actually start with a new molecule and let the name work backwards. All right, so I just created a new page, and I'm going to file and then import by a chemical name. And I've tried a few things. It actually is pretty good at even common names, because aspirin is definitely a common name. But if I type in aspirin and hit go, my computer's a tiny bit slow, but it does indeed find it. Now, it is mostly just a structure based on average angles, so the structure has not been optimized. So whenever you come up with a structure, a new structure, you are going to want to come up with the optimization tool and tell it to fix that structure. Now this is kind of interesting because looking at it, see this O, bringing it in closer and closer to that. I wonder if we can just grab hold of that Oh, that's not what I wanted. And pull this around. Where was I pulling that at? Yeah, all right. So I got it kind of behind. And I'm going to actually pull it some more. So it's over here. So I knew that that auction is going to be giving us some strain just being close to there. But I got caught in a little pocket of stability. It's we're going to see later on. We call those conformers, and that's why it was locked into place fine there. But if I gave it a chance to move it around, it got those auctions far away from each other. Still optimizing the structure to making ever so slight changes. All right, and it's done. All right, so I'm going to stop my optimization. Now, all you're going to do is actually do the structures of, I don't remember. What does the lab say? I did 2-fluorobutane and salicylic acid. And I want you to generate an electrostatic potential map for both those. And what you're going to do with that electrostatic potential map, go to back when we have it, just get a good picture of it. So I'm just holding my mouse down and twisting it so we can see a general layout of the structure. And then you're just going to come up here and export a graphics. And it's going to choose a PNG. Just give it a name. I'm going to save this to my desktop. I'm going to call it 2-butanone. Actually, I'll call it what the mean sheet said. Butan 2 dash. And here's something interesting. Even though we know that this was aspirin because we typed it in, if we go here to our properties, it's going to give us something closer to the IUPAC name. So 2-acetyl oxybenzoic or acetoxy benzoic acid. Okay, now for now that's all we're doing with Avogadro. But in class here, very quickly, we're going to start and we're going to do something along with the conformer search. And once I get a better version of this program, I was going to actually incorporate this into this lecture so we don't even have to use Falcio at all anymore. All right, speaking of Falcio, that's what we're going to go to now. So I'm just going to close this stuff, discard, and discard. And I downloaded and extracted Falcio and Firefly, and they were in this downloads folder. All right, so to get the Falcio, I keep pronouncing it wrong, open, we just go into the Falcio directory and then run that program. Now, the very first thing we're going to need to do is go here to Preferences and External Programs. Now, Falcio has a lot of things. Falcio has a lot of things it works with. Tinker is a different way of manipulating structure, same as MSMS. And all these that says games, they're all derivatives of a program that was started ages ago, and it's just branched off multiple cases. The only thing we need to change on this entire page is the pathway to Firefly. So I'm going to hit Browse here, and I put it in my Downloads folder under Falcio FF, and there it is, Firefly 810. And I'm going to hit Apply and Save. And it's going to tell me all the ones that weren't in there, but that's okay. We didn't actually put any of those in. All right, now we're ready to actually do a structure. Now on Falcio, there already is a very large library of structures in there. If you go to the Falcio folder and then the folder that says PDB, that's protein database. And even though we're not actually doing proteins, there's a bunch of things already programmed in here. So I'm going to look at acetone, for instance, because it's a simple molecule. All right, and that's what it looks like in Falkio. All right, now just like Avogadro, we're going to optimize the structure and get the bond lengths the same. Now, this is going to be a different program, and it actually does take a little bit longer because it's actually doing the calculation a lot more. Um, they call it from first principles, so it's a lot more detailed calculation. Um, Avogadro was trying to kind of teaching the treating the bonds almost like springs, and the atoms themselves as charged balls, and was using more like classical physics to separate them around. Um, the ab initio programs like Firefly are using mathematical formulas and curves to represent the bonds, and we're going to actually optimize those. So this calculation will take a little bit longer, but we're going to start up our calculation. We're going to choose that Firefly, and something we need to do to make this a little bit more trustworthy on organic chemicals is the only option we have to change in all this right now is this G basis, and we want to change this to the N311. Technically, the N21, N31, and N311 would actually do a decent job, but I just go ahead and go with the, and it didn't change, did it? Okay, there it goes. And that's all we really need to change. Nothing else needs to be changed right now. It did default to optimize, so check all the defaults were fine. And I just hit execute. This is going to take noticeably longer than Avogadro did, but it's not prohibitively long. I'm going to pause my video while that finishes up. Okay, as soon as it was done, the screen went away, and we have this new update in this worksheet. And what we're looking for is just saying that it terminated normally, and there's really no reason why you shouldn't expect that. And it gives you a bunch of these numbers on it. But the structure ever so slightly changed. All right, now something we're going to do differently on this, just to show you some of the versatility of these ab initio numbers. We're going to now do another calculation with Firefly, but we're going to get something to help us actually predict vibrational stretches or vibrations of the molecule itself. So what we need to do is actually study the entire curve of all those mathematical formulas I talked about. So we said we're letting the math here was using curves and such to represent the bonds, and we were optimizing those curves. Well, this Hessian here is going to vary them slightly, so we can see the effect of changing them. So only thing I need to do is change that to Hessian and hit execute calculation again. This time's going to take a bit longer than the first one. So I'm going to pause this video again, but actually before I pause it, what I'm going to explain going on here. So we're modeling our atomic orbitals with little shapes. Well, that actually went a heck of a lot faster than I thought. But that's okay. It did actually give me a good execute. All right, but it actually allows us to adjust the calculation based on if these things move or vibrate. Now, technically, all molecules vibrate, and vibrations can be visualized if you know those curves. So now that we've actually done that Hessian, this normal mode vibrational viewer actually popped up as an option. All right, now I'm just going to leave this at nothing. I'm not changing any of these numbers up here. Only thing I'm going to do to show you what this is doing is hit this here, calculate animation frames, and then hit start. See how the molecule started vibrating? That's what we're actually seeing. And if I change the normal mode, I get a slightly different animation. So we're seeing the various different ways this molecule absorbs or gives off energy by vibrating. And so far it is really just the whole molecule itself moving and vibrating, because those are always the low numbers. But as I go higher, and I will just go ahead and go quite a bit higher, I'm going to see it's very limited in what moves. See, once I'm up here, it really is just this CO bond vibrating. And if I go up even higher, we actually start seeing those are just the hydrogens. Still just the hydrogens. Still just the hydrogens, but slightly different motion. Kind of weird. All right, where this comes in handy for the organic chemist, when we actually want to study molecules or identify them, it'd be nice if we could actually visually see these vibrations. Well, obviously we can't. They're too small, but we can see the results of them because it turns out these frequencies they're talking about, they all pop up in the IR spectra. So if you had an infrared spectrometer, you can actually see the actual spectra of that given molecule just from these predictions. Now, here's something weird. Even though we know for sure that that calculation is done with some really good formulas and really good equations, these vibrational frequencies are always predicted to be a little bit high. But fortunately, it's very predictable height. So back in 2007, these people figured out, all right, here's the best way to scale them. And we're going to scale it based on the code we use. So even though that Firefly said N311, that is a Hartree-Fock 6311 value. And technically, that vibration we saw where the oxygen and hydrogen was moving is this one that is that most intense peak on this slide and happens right around 1710. Now that on this vibration, calculation-wise, it showed 18. And I've covered up the picture, but that is just that CO double bond vibrating very, very rapidly, and it shows up around 1710. Now, on this one on your lab, I've asked you to do it for salicylic acid. So you would put salicylic acid into it, and you do that exact same calculation and see if that CO shows up in about in the same location. And it actually should. It should show up around 1710. Now, if you notice though on the page here, I have it blocked off. Biggest reason I have it blocked off is these two programs are getting to Falkio is getting to the end of the life of it. And even though this was released in 2018, and we're not even 2 years old yet, there is a chance this version's not going to work for you. And Windows 10 probably won't take this version at all. So if you have any trouble getting Falkio to start running, don't waste your time with it. Just give up, and that's why it's been marked out. Now, hopefully I'll be able to figure out how to get this all working with Avogadro. Avogadro technically can do these vibrational frequencies. I just have to get a couple more programs set up. And that's taking some registration and asking the right questions of the right people. But hopefully we'll be revisiting this vibrational frequency when we get to our lab that deals with infrared spectrometers, because that's what this is dealing with. So later on this semester in lab, when we do IR, it'd be wonderful we actually could use this to simulate a infrared spectra and then see how well it compares to the real thing. All right, so fortunately for you, about the biggest thing you're going to do is Avogadro for the 2-fluorobutane and salicylic acid. Get me some electrostatic potential maps and print that out. Be sure to play around with that program some. We're going to be using it some even in the class because it can help us visualize some things. Okay, have a good day.